Hello everyone. So here are the notes for today. They are going to be titled Trig Functions. So today we're going to learn about the 6 trigonometric functions. Define them, what they are. 3 of them should not be new to you guys. The other 3 might be new to you guys. So what is trigonometry? So pretty much trigonometry is the study of the relationships among the sides and angles of triangles. And the trigonometric ratios specifically, those compare the lengths of 2 sides with respect to some type of acute angle, which we call theta, in a right triangle specifically. And a trigonometric function is pretty much a rule that is defined by using our trig ratios. So it says, using the triangle to the left, we're going to determine and define the 6 trigonometric functions. So the 6 trig functions are either sine, cosine, cosecant, secant, or cotangent. The 3 that you see on the left, sine, cosine, and tangent, those should look familiar. Cosecant, secant, and cotangent might look brand new, but they're actually not super brand new, and I'm going to show you guys why in a second. So we're going to answer and we're going to set up all these ratios in regard to this triangle that we see right here, where I have my angle theta, I have my right angle, and then I have my 3 sides. So in regard to angle theta, obviously this side right here is my opposite because it is across from it. This side down here is my adjacent because it is my side that is next to my acute angle and it touches my acute angle. It is one of the sides that forms my acute angle. And then obviously my hypotenuse is the side that is across from my right angle. Again, that information should not be new to you. Okay, so what is the sine function defined as? So the sine of theta is equivalent to the opposite over the hypotenuse. The cosine of theta is defined as the adjacent side over the hypotenuse. And then the tangent of theta is defined as the opposite side over the adjacent. Okay, and for sine, cosine, and tangent, they have come up with the very handy dandy acronym SO, CA, TOA, right? Which I know that you all have heard before. So the sine is opposite over hypotenuse. The cosine is adjacent down here over hypotenuse. And then the tangent of theta would be opposite over adjacent. Okay, now what are these other ones? Cosecant, secant, and cotangent. Well, those are actually defined as what we call the reciprocal of the function that's given to it on the left. So cosecant is defined to be the reciprocal function to sine. What does that mean? That means that the cosecant of theta would be defined as the hypotenuse over the opposite. So literally what I did was I took the sine function and I just flipped it. I took the reciprocal. The secant function of theta would be defined as the hypotenuse over the adjacent. Again, what I did here was I took the cosine function and I just took the reciprocal. And then lastly, your cotangent of angle theta would be equal to the adjacent, over the opposite. Okay? And that's what brings in this idea of reciprocal functions. So it says, because the cosecant, the secant, and the cotangent ratios are reciprocals of the sine, cosine, and tangent functions, they are what we called reciprocal functions and can be defined as this. So cosecant is equivalent, the cosecant of theta is equivalent to 1 over the sine of theta. The secant of theta is defined as 1 over the cosine of theta. And then lastly, the cotangent of theta is defined as 1 over the tangent of theta. So cosecant, secant, and cotangent are just reciprocal functions to the 3 trig ratios that you all are already familiar with. Okay, so what we're going to do in this first set of notes is really just become familiar with creating these ratios. Again, this should hopefully not be brand new information to you. Number one is super easy. I'm going to go through it super fast. And then I'll probably help you guys also with number two. I'll set you up for three. Actually, no, I probably won't do two. I'll probably do number one because that's the super easy one. And I'll probably do four here just so that you guys can get a little bit more complex, and then we'll do some of the other ones. So on this first one, let's start with number one. What we're going to be doing is we're going to be finding the exact values of the 6 trigonometric functions of theta. So let's start off with number one. And number one, this is considered an easy question because all of my sides are already given to me. I don't have to solve for any of them. All I'm doing is going straight into creating the ratios. So let's start off with the sine of theta. Here's theta up there. I want to go ahead and create the sine ratio. For sine, I use opposite over hypotenuse. So the opposite to theta would be 12, and the hypotenuse is across from the right angle, so that would be over 13. So 12 over 13 is my first ratio. Cosine of theta. Cosine of theta, I look at my angle theta, and I have to do adjacent over hypotenuse. So my adjacent side would be 5. My hypotenuse would be 13. So this ratio would be 5 over 13. If these fractions could have been simplified, we would have had to have simplified them. But in this question, nothing can be simplified, so I just leave it like that. Tangent of theta. Here's my angle theta. Remember, you create trig ratios in regard to a specific angle, an angle theta. If theta was down here, these ratios would be different. So you have to create these ratios in regard to the angle that's given to you. So in angle theta, I have to do opposite over adjacent. So this would be the opposite, which is 12, over the adjacent, which is 5. Again, nothing can be simplified, so I'd stop there. Now let's go ahead and create the cosecant, the secant, and the cotangent ratios. The cosecant of theta is pretty much me taking the sine ratio and just taking the reciprocal of it. So rather than 12 over 13, that would be 13 over 12. The secant, that's the cosecant. The secant would be taking the cosine and taking the reciprocal, so this would be 13 over 5. And then lastly, the cotangent would be taking the reciprocal of the tangent, which would be 5 over 12. Okay, hopefully that was easy enough. If you have any questions, let me know. This one is a little bit tricky because you have a square root there, but I'm going to actually do number 4, which already has a square root, and then whatever I teach you guys in 4, apply it to number 2. This one is, I'm not going to do it either, but what makes this one difficult is if you notice here, they give you 20, they give you 29, but they didn't give you this bottom side. So your first step is to use the Pythagorean theorem, which remember is a squared plus b squared is equal to c squared. Solve for the missing side, which remember in this one, this c is always the hypotenuse, and then a and b are any one of the legs. It doesn't matter which one you put as a or as b. Once you have the 3 sides, then you create your ratios. Okay, I'm not going to do that one for you either because that one's doable. Let's talk about 4. So in number 4, first of all, this one's difficult, right? Because you're missing a side and it also has a square root. So this will be a good example for me to go over. Once I do this one, you should be able to do 2 and 3 yourself. So let's first solve for a missing side. I need to realize here, which side is this x? Is that a leg or is that the hypotenuse? Remember, these two, A and B, are legs. C is always the hypotenuse. So in this question, they give me a leg. And then what I'm missing is the hypotenuse. How do I know? Because it's the side directly across from the right angle. So to solve for that missing side, I'm going to say 6 squared plus 6 square root 3 squared is equal to x, or we can call it c squared. It doesn't matter. Now let's go ahead and let's solve this one. Right here, I am going to get, you need to realize here that the 6 and the square root of, so 6 squared we obviously know is 36. And then right here, we need to go ahead and apply this 6 to this squared. I need to apply it to the 6 and to the square root of 3. So let's first do 6 squared, which will obviously give me 36. And then square root of 3 squared, that square root and the squared eliminate, so I'm just left with 3. Is equal to c squared. Now let's just do this algebra. 36 plus, what's 36 times 3? Just use your friend Desmos, 36 times 3. Gives me 108 is equal to c squared. Let's take 108 and let's add 36 to it. Gives me 144. Last step to get c by itself, square root both sides, and you get c is equal to 12. So my missing side here is 12. Now that I know all my three sides, I can create my trig ratios. Let's start with the sine. Sine of theta. Where's theta? Theta's down here. So to create the sine, I need to do opposite over hypotenuse. Opposite over hypotenuse. So that would be 6 square root 3 over 12. Here, what can be simplified? You need to simplify. The numbers on the outside, those are just integers. Those can be simplified. The 3 cannot be simplified with the 12 because the 3 has a square root with it. That is its own term. However, the 6 and the 12, those can be simplified. 6 over 12 can simplify down to 1/2, which would just leave me square root 3 over 2. So if I know that one is square root 3 over 2, what is cosecant? Well, cosecant, I have to just take the reciprocal. This would be 2 over square root 3. However, you cannot stop there because you can never, ever, ever, ever have a square root in the denominator. So in order to eliminate that, you have to do something that's called rationalizing the denominator, which means you multiply both the top and the bottom of the fraction by whatever is down here. Whatever's down there, you multiply both the top and the bottom by it. Now, what happens here? Well, 2 times square root 3, I cannot multiply those because one is a whole integer, the other one has a square root with it. So this would be 2 square root 3. I just write them side by side like that. Over at the bottom, what happens there? Well, I have the square root of 3 times the square root of 3. Though, since they both have the square root, I can take what's on the inside and multiply it. So this would be square root of 3 times 3 is 9. And what is the square root of 9? Well, it's 3. So one trick that you can think of is like you can actually work it out like this and get 3. Or if you want to kind of be lazy, you know that the square root of 3 times the square root of 3 essentially just gives you 3. If you want to think a version of it that these like eliminate, you can kind of do that. It's not really that's what happens, but it's the process of rationalizing a denominator, which kind of just gives you what's left in the inside. So this would be 2 square root 3 over 3. And yes, you do have to write your answer like this. If you give me this, I'm not giving it to you because that is like the number one rule in math. You never, ever, ever, well, it's probably not the number one, but it's a rule in math. You can never, ever, ever have a square root in the denominator of a fraction. Okay, so let's go ahead and come up with the ratio for the cosine of theta. Cosine of theta, you use adjacent over hypotenuse. So that would be 6 over 12. 6 over 12 can be simplified down to 1/2. So if the trig ratio for cosine of theta is 1/2, then the secant of theta would be obviously the reciprocal of 1/2, which is 2. Tangent of theta. Tangent of theta is opposite over adjacent, so that would be 6 square root 3 over 6. 6 square root 3 over 6, the 6's eliminate, and it just leaves you with square root of 3. The cotangent of theta will be the reciprocal of the tangent, so that would be 1 over square root 3. Remember, you can never, ever, ever have a square root in the denominator, so you must rationalize, which will leave you the square root 3 over 3. All right, with that logic, you should be able to do 2 and 4 now. Let's go on to the other ones. Now, in these ones, you're still going to come up with the trigonometric values. But if you notice here, they do not give you a triangle. Instead, they just give you one ratio. And from this one ratio, you need to create a triangle. So I will go ahead and do like number 5 and number 8 here. So let's create a ratio for number 5. Let's create a triangle for number 5. You can create and draw this triangle however you want, just making sure that this ratio works at the end of it. So I'm going to go ahead and just draw a very basic triangle. Here's my right angle. And I'm going to go ahead and put theta down here. It doesn't matter where you put theta. Just make sure that you put the sides in the right place. So we know that the tangent of theta, is equal to 7 over 4. And we know that in tangent, you use the sides of opposite over adjacent. So from theta, I know that its opposite side is 7, and I know that its adjacent side is 24. So the only side that I do not know here is my hypotenuse, which is x. So in order to solve for x, again, you use the Pythagorean theorem. You use the 7 squared plus 24 squared is equal to x squared or c squared, whatever you want to call it. This, when you take the squares and you add them, you end up getting 625 is equal to x squared. And then you can square root both sides, and then you get x is equal to 25. So the missing side here is 25. Now that you have that, you should be able to do the questions like you did on the front side of creating all the trig ratios. Make sure that you simplify down your fractions and you rationalize any denominators. Let me go ahead and help you guys with number 8, because number 8 is a little bit different. Number 8, again, all they give you is one trig ratio, and you need to go backwards and draw the triangle so that you can create your trig ratios. They give you theta. It doesn't matter where you put it. I'm going to go ahead and just put it down there. But they give me the secant function. So in order to do this one, you need to think back. What is the secant the reciprocal of? Look back at the top in case you do not remember. The secant function is the reciprocal of the cosine function. So secant is hypotenuse over adjacent. Why? Because cosine is adjacent over hypotenuse. So in this case, secant would be, rather than adjacent over hypotenuse, it is hypotenuse over adjacent. So this one, even though it's not a fraction, you can put it over 1. So what this ratio is telling me, it's telling me that my hypotenuse is 4. So this number right here is 4. And my adjacent is 1. My adjacent to what? Well, my adjacent to theta. So this side down here would be 1. Now, to solve for the missing side, use the Pythagorean theorem again. Again, you have 1 squared plus x squared, because this is the side we don't know, is equal to 4 squared. This will give you x squared is equal to 16 minus 1 is 15. Then you square root both sides. You get x is equal to the square root of 15. So your missing side is the square root of 15. Now, with that logic, you can go ahead and create your ratios. Again, making sure that you rationalize any denominators. Obviously, the one that you don't have to work out is like the secant of theta. You already know what the secant of theta is. The secant of theta is 4, because that's what the original question gives you. Same thing over here. You do not have to work out the tangent of theta. You already know the tangent of theta is 7 over 24, because that's what they give you in the original question. But you should check it that your triangle lines up. Okay, hopefully you should now be able to do the rest of 5 through 8. Let's do this bottom half. So trig values using special right triangles. So this is something, again, you should have learned in geometry. If you didn't, well, now's your opportunity. Ask questions if you have them. So there are 2 special right triangles that you should have learned in geo, the 30-60-90 triangle and the 45-45-90 triangle. So angles of 30-60-90 and 45-45-90 are frequently used in trigonometry. You can use your knowledge of these side relationships and special right triangles to help you find the values of trigonometric ratios. So in these special right triangles, essentially these are triangles where if I just give you one side, you can solve for the other sides without using the Pythagorean theorem. Now, why is that true? Well, in a special right triangle like 30-60-90, there's rules here in regard to the sides. You always know that the side across from the 30 degree is always what we're going to call x. And then the hypotenuse of a 30-60-90 triangle is always 2 times x. So it's always double the shortest leg. And then the side across from the 60 is always x times the square root of 3. Now, again, if this is not ringing a bell to you, then it's probably because you just don't remember 30-60-90 triangles from geometry. I can prove to you guys why this is true, but it's kind of a lot of work. So maybe in class I can show you guys. It's essentially you have to prove it through like constructions, through kind of building like a second half here of a triangle and using side angle side similarity to prove it. Again, I can prove it to you in class if you'd like, but if not, watch a YouTube video on it. But yeah, that's what a 30, 60, 90 triangle tells you. It tells you that if you have the side across from the 30-degree angle is always x, the hypotenuse is always 2 times x, and then the side across from the 60-degree angle is always x times the square root of 3. All right, now what about in a 45, 45, 90 triangle? Well, in a 45, 45, 90 triangle, you know that this is an isosceles triangle because 2 of the sides are the same. So if 2 of the sides are, 2 of the angles are the same. So if 2 of the angles are the same, 2 of the sides also need to be the same. And the 2 sides that are the same are the legs. So the legs are always equivalent in 45, 45, 90 triangles. And then the hypotenuse is always the leg times the square root of 2. So with that logic, you should be able to easily come up with the ratios of 30, 60, 90 and 45, 45, 90 triangles. Now, why is that true? Well, the sine of angle 30. So the sine of angle 30 is always going to be equal to 1/2. Now, why is that true? Well, look at it. Angle 30 is down here. Sine, you use opposite over hypotenuse, which would be x over 2x. Right here, your x's eliminate, and all you're left with is 1/2. So this is always true. The sine of angle 30 degrees is always 1/2 in a 30, 60, 90 triangle. The cosine of angle 30 is always square root 3 over 2. Now, why is that one true? Because for cosine, you use adjacent over hypotenuse. So that would be x square root 3 over 2x. Your x's eliminate. And what is the only thing you're left with? Square root 3 over 2. And guys, I cannot emphasize you enough how important this is going to be later. So these 45, 45, 90, and these 30, 60, 90 trig ratios, get them down. Understand how to solve them. And it'll be easy once you really understand these relationships here. Okay, with that logic, try to figure out the rest of this chart. I want to challenge you guys with you guys trying to determine the ratios first, and then we will go over them in class. And more specifically, we're going to really emphasize this a lot, and I'm going to conceptually go over this a lot more when we do the unit circle coming up next. But continue to try these. All right, let me know if you guys have any questions on coming up and creating the 6 trigonometric ratios for right triangles.